because I don't know what happened to Zaina, but maybe she's in the bathroom or something. I don't know. She's on her way here. Okay, so what I want to do is I wanted to, in this lecture, I wanted to tell you a bit about the development or what are called cubicle type theories. And I'm doing it from the point of view of the computational type theory, so we call it computational cubicle type theory. And in fact, to distinguish one particular feature of it, which I'll mention shortly, we actually call it Cartesian computational cubicle type theory, or computational Cartesian cubicle type theory, or something. So it becomes CCCTT, and we sort of write that down a lot. So that's what I'm going to tell you about, which is our particular brand. So it's approached from the point of view of programming languages. So I started out my lectures by saying, you know, the kind of the premise of constructivism is that sufficiently expressive programming language is a foundation for mathematics, and I've always been inspired by that idea. So this is a kind of development of that. Okay, so where we were last time is the thing I want to motivate last time. So recall, we defined the notion of this so-called identity or identification type, which we have here. So this would be called, was for a long time called the identity type. Sometimes now it's called the identification type for reasons that I mentioned last time. And ab initio, I should say, its introductory form is just reflexivity, which would have type id-a-m-m, assuming m is actually in there. And that's an unproblematic thing. And then there's an elim form that witnesses, as I mentioned, that it is to be thought of as the least reflexive relation. So I won't belabor everything here again, but we had something, I think I called, I don't remember how I used my letters, pardon me, Q, where this identity in A of, let's call it M1, or I think I'm more often used, well, anyway, M1 and M2. And the idea is that its type in the formal setting is you plug in M1 and M2, and you plug in Q in this case for A, B, and C in capital C. So that was the idea that since this is of identity, you're sort of saying this identification or identity equals fact. Okay, so that's how you're expressing the universality. And so that was around for a long time. And in that context, as I mentioned, Martin Liff proved some theories about the type theory containing this, and proved that, in particular, Martin Liff in around 72 showed that if you have anything in the identification type at any type, and they're closed, everything is then have to be definitionally equivalent. And that turned into a problem because if this is a function type or a pi type, then it's not exactly what you were hoping for. You kind of would hope that the equality, the type representing some kind of equality, identity, whatever word we want to use, ought to identify functions extensionally. The reason being, well, that's what you, I think, always do in math, more or less, as far as I know it, which, okay, and so people often find it deficient in this respect. So there were two ideas we talked about, and we talked about one, which was which people do a lot as long as they don't care about computation, adding in extensionality for functions, sort of manually. And then the other thing we talked about was adding what is called the univalence axiom. Okay, so the univalence axiom being an identity in a universe which identity between two types whenever, and I didn't go into a lot of details here, whenever we have an equivalence, which is some kind of, you can think of it as an isomorphism, okay? So we added these things in, and for many purposes, that's a fine thing. You can treat type theory as any other axiomatic theory and care not a damn about the computational meaning, and then as far as I can tell, I guess you're okay if you do that. But I wanted to look at it from a computational point of view, and where we left last time was saying, well, with the function extensionality, that's relatively easy to deal with. We can interpret this as exact equality, and then everything comes out for free. But here, there's no chance of interpreting that for exact equality. And the reason is that there's non-trivial evidence and it matters. Okay, types can be equivalent to one another in quite a variety of ways. And so the question is this, and what motivates it is the following thing. A nice thing that gives me a jumping off point is we can define something called the transport operation. So this is a sort of A-index family of types. I'll just write family. So the examples I was giving, were things like, it wouldn't be so interesting in this case because of the use of transport, but remember that families of types were things like vector of length 17, okay, and we have other things. But in general, if we define types to represent relations about anything at all, of any type at all, then those are families of types. Any property or relation that you care to be formulating in type theory will have that form of being an A-index family of types when the objects of discussion are of type A. So in particular, we have this notion of transport map, which if given a proof that, let's say, M and N are the same elements of A according to this notion of identity, then it turns it into a function that goes from f of m to f of n, meaning m for A and n for A here, writing it shorthand, okay? So the idea is that certainly at the level of, so it can define this, and you can define it using J. And you can look it up, I can write it down, it's actually, I'll write it down. So the argument is you do this and you'd write f of A or f of B, that's my capital C, which involves, in this case, A, B, and I don't care about the proof. Okay, and the P part is just the identity function on f of A. And then you write capital P, and you can check, okay, that this is how you do it. So you define transport. So we can write it like this. This is defined to be that, okay? So it has the flavor of being, so the idea of transport is supposed to be, if I have an A-index family of types and I have an identification of two elements of that type, then I ought to be able to, and then you can read it many ways, but one way is you say, if I have a proof of f of m, then I'll turn it into proof of f of n, because after all, m is n, so why should that not be the case? And moreover, it should be reversible, and you can define structure here that shows that you can reverse them, you can concatenate them, and they have all the right properties. Okay, there's a lot of stuff you can do. But what happens is, so that's the setup, and this kind of thing is, part and parcel of using type theory with this kind of identity type. But when you do what is called in hot, so here is, this became known as homotopy type theory, as a particular formalism. And there is a book, like more often people will say hot. And so I'll call it, and I'll emphasize I'm using the term hot to refer to the formalism rather than some general program. I just want to mention the formalism. So it's sort of adding in like the univalence axiom, because it turns out it gives you function extensionality by a kind of clever argument of Voevodsky's that shows that. So I don't actually have to add that. And actually there's a third thing, which I probably will not be able to discuss at all, which are inductive types with identifications. Think of it as, roughly speaking, think of it as defining an inductive type that's quotiented in a certain way. And the quotienting is represented by the existence of identifications of elements of that type. So I won't say any more about that, but that's essentially the idea. So instead of having purely freely generated, it can be freely generated, so to say, modulo some equations, except they're not equations, they're identifications, and the identifications are proof relevant. Okay, there's a whole story there, but I won't be able to explain that in any detail here, okay? But those are the three things, and because this follows from that, then most often the hot formalism is considered to be this, and it's not sort of entirely clear what class of inductive definitions, and people have been working on that, so, okay, that's cutting edge, but let's just say that's what we mean. Okay, so the problem that we have here, though, as I mentioned last time, is what is, and we can, it's actually an instance of J, but if I look at, let's look at the following thing. If we look at, first of all, if I consider sort of the identity family, as long as I have universes, I can do this, the identity family, okay, A dot A. So it's a U-index family of types, and the elements of U are types. So A dot A is a very reasonable family. Okay. Then what happens is, if you look at the transport in A dot A along a path whose is an identification of two types, I call it A and B, then if I just crank out what I said here, I'm going to get an invertible function from A to B, which is very tempting to call a coercion. It's a kind of coercion function. And again, it makes perfect sense. If I claim that A and B are equal or identical as types, then I certainly ought to be able to take any element of A and turn it into an element of B. And I will compare this to the rule for, in formal type theory, it would be the preservation of definitional equivalence, preservation of typing, under definitional equivalence. If you curry the rule and say, if A is definitionally equal to B, then anything in A is also in B. So saying the identity map is a map from A to B, okay? Or in computational type theory, it looks just like a notational difference, although it means something different. If I have exactly equal types and I have an element of A, then it's also an element of B. So this is kind of saying if I have so-called identical types, so what we're doing here is it's almost like saying, write this down as an assertion. If A and B are equal as types, well, the point is that involves data, so I'll get to that. But it looks something approximately like if they're equal as types and I have M and A, then, well, something derived from M ought to be in B. And so the setup is you give evidence and then you transport, let me just abbreviate, say transport along M, gives you something in B. So it's a direct analogy here. That's the idea. Okay? And I won't go into the development, but you can prove, as I remarked, that the transport is reversible and it's composable. You can compose two of them. So it starts to look a lot like some notion of equality or some idea of equivalence in a certain way that is proof relevant. Okay? That's the idea. So the thing that comes up is, so the idea that comes up here is identification, a motivating thought as sort of proof-relevant equality, if you don't mind me like speaking so like that. Okay, maybe it will help you. Okay, you could say, by the time you call it equality, you can't call it proof-relevant, but anyway, I'll put it in quotes, and that way that's my disclaimer. So it's just a way of saying, like, you're supposed to think of it as like things that can be interchanged. So if equality means things can be interchanged, then this is a notion of interchange, except that it matters a lot exactly how and why things are going to be equivalent. We look here now with this situation. Okay, so if I look at this guy here, this guy, if I look at, for example, the instance of this at univalence, which is such a path, okay, the question that I mentioned is, what does that compute to? Like, what the hell is going on here, okay? If I have this idea of transport, which is derived from J, and by virtue of being derived from J, transport knows what to do on reflexivity. That's no problem, okay? But what is the poor guy supposed to do with UA? Or we mentioned last time motivation funnext of a H, or when we have higher inductive types, you'll see there's a formal path called, or identification called the loop. So these kinds of examples will come up, but we'll focus on this one, okay? And so the problem is you don't know what to do with that guy, okay? So the point is that from a computational point of view, it's stuck. It's a well-typed thing that doesn't simplify away. And the result is that you can't prove anymore that if I have a closed Boolean that it's definitionally either true or false. That's out. So that's a peculiar thing, okay? Now, the setup that you get can be justified in completely other ways besides computation, and maybe you're satisfied with that. So Vladimir in the beginning gave a model in using what are called simplicial sets, a combinatorial way to talk about spaces. And for many purposes and people, that's perfectly satisfactory. But that just isn't my enterprise, okay, what I want to do here. Okay, so the question is that, okay, we're stuck. So if this is supposed to be a coercion, I'm using that terminology suggestively because every computer scientist at one time or another comes across the idea of a coercion. And every single person who's ever written down a programming language, it seems to me, eventually comes up with reinvents the idea of a coercion. It never really works, but but I just want to use that as a kind of way of priming the pump of your thoughts. So if this is supposed to be some kind of coercion, what in the hell, how is it supposed to work? Like what should be here? Okay, well, it's not very obvious how to do it, but the idea ought to be to apply the equivalence, right? Because UA is generated by E, which is an equivalence, which consists of a whole bunch of data, but at the very least, at the start, it's a function from A to B and a bunch of other data, which I'm suppressing, that more or less says it's invertible. Okay, so what it means is, the way it's done, and I'll show you shortly, it means that every element of B has a preimage that is a singleton, essentially. If you think about it, that's one way to say one-to-one and onto. There's a map from B to the preimage of, under F, which is non-empty and really contains only one element. Everything is equal to it. The actual definition we'll get in a minute. They're actually identified with, but never mind that. Okay. So equiv says this is a function which is, I more or less will say, a bijection. I'm speaking loosely. Okay? That's what an equivalence would be. So this guy, I mean, after all, if E goes from A to B and I'm treating it as if it were a witness to the equality of A and B, then by God, if I want to go from A to B, how the hell else am I going to do it? I'm going to apply the equivalence. Right? Common sense, okay? But now is the rub. The rub is the identification type is defined in a type-independent way. If you look what I summarized back here, this is completely generic in A. It doesn't matter what the type A is. It's going to do the same damn thing every time. You have reflexivity, fine. Put the A on there. I don't care. That has more to do with type checking considerations. You're just going to plug in M for little a and P, and that's the answer. And that's it. It just works like that. It works in a completely generic or type-independent way. But if I'm going to have it mean something about coercion, I have to say when the type in question is U. Because only then does this path even come up. It's not type independent at all. Reflexivity is sort of type independent. The univalence axiom depends on it being identification in U in the universe. Or if I had function extensionality, it depends on it being a function type. Or if I have these other things, it depends on the particular type. So it's totally the opposite. It's type specific. And the issue is, how the hell do you resolve that? Okay? How do you make this work? Well, I'll foreshadow. It can't, in my opinion, it cannot be fixed, as stated. Okay, so the hot formalism, I think it's sort of a consensus now. I don't know. There doesn't seem to be any way to make it to recover a computational meaning. What you have to do is you have to make a Martin-Liff ninja move, okay, which some of you know about, okay? And you kind of change to a different arena of discussion. And the idea is the following thing. You can feel, if you have experience in type theory, and I think I alluded to this last time, if you have experience in type theory, as soon as somebody starts telling you they're going to chuck in axioms in type theory, you have to be suspicious. Now, I told you that with respect to formal type theory, you take advantage of the fact that it's merely a recursive enumeration of some structure. And therefore, it's very weak, not very expressive. And therefore, you can get away with strange things in certain circumstances if you know what you're doing. And Vladimir knew what he was doing, okay? Which was, you can throw in these new equational axioms, and it at least makes, quotes, mathematical sense. The question is how to make computational sense. So what we do is we apply, so I'll say it in a certain way, which has to do with my worldview. Okay, this is just like expository thing. So I will say the idea for me is adding axioms is suspicious. Okay, It's just not the way you're supposed to do things. Okay, meaning axioms means elements of a type. So I'll give you an example of this because there's a kind of lineage here, which I'll be brief about. There's probably a huge lineage, but I'll just mention a couple things. The main thing was like Gensen, and in a certain sense, I'll say versus Hilbert. If you pick a conventional math logic textbook like Schoenfield's book, the way they do things is, one of the things they do is they start out with a bunch of weird-looking implications as axioms. Okay, one of them's not too bad, A implies A. Another one is A implies B implies A. And the third one, I can probably think hard and write it down correctly, but it's like, until you know some secret, which we can talk about another time, it's like the most obtuse thing ever, okay? But you can do it. In other words, he populates the function type, the implication, okay, with proofs, and you just write down these things, and voila, these are supposed to be exactly all you need. Where the hell did that come from? Gensen said the idea is this, is that, I'm, of course, briefly summarizing. Entailment is prior to implication. In fact, Gensen invented this. And this is why I call it a ninja move, because it looks really strange. You have an entailment, A entails B. This is a logical consequence relation, or entailment. If A entails B, then you can say that A implies B holds. And those are different things. Try to explain this. Like if you study logic, if you study proof theory and stuff, the kind of things we teach here, it's the most natural thing in the world. Okay? Try to explain it to your colleagues. Good fucking luck. You're not going to get anywhere. Okay? I know from experience. Okay, so it's very difficult to, that's why I call it a ninja move. There's a ninja move here, which is focus on entailment, not implication. People say to you, well, what the hell is the difference? Well, there's a big difference, but let's not go there, okay? Right. A very related thing is Eilenberg and MacLean. Which is that maps are prior to function. And it can even be made to look like this, but it says, if I have a map from A to B, well, really, let's say C cross A to B is the way it's usually done. That's like putting in all the gammas. So if I put in all the gammas, it would look like this. So that's my gamma. After all, gamma is C, isn't it? Okay, so I have C cross A, and I have a map from B. Then you have a particular, whoops, it usually goes over here. I'll just write corners that for something. Okay, is a map from A, C arrow B to the A. The exponential is a different thing from the maps. So the HOM comes first. Okay? It's the exact same idea. There's no difference. It's really just the exact same. So here, the Martin Leff style move is bring out, so what I want to say is that this logical constant equivalent is called the hypothetical judgment. And that's exactly what's going on with maps in a category theory. It's the analog of a hypothetical judgment. I judge that this is a map from C cross A to B, and then I can turn that into a map from C into this exponential. So you first make the judgment structure first. So the idea is to bring out the judgmental apparatus, the judgmental structure of identifications. Then you can internalize them in a type. See, in both cases, this is a kind of internalization. The external, if you will, entailment is internalized by the connective, A implies B. The external idea of a map is internalized, if you will, by the exponential object B to the A. Okay? So we use the word internalization for that. So what we want to do is we first want to talk about order identification, in which it's easier to call them paths for a reason I'll explain. Okay? Then you internalize them as a type. And what will happen, if you want to know the end of the story, what will happen is it'll bifurcate. We get id will emerge as an inductive type. The reason I emphasize to you that J witnesses that the identification type is the least reflexive relation is because I wanted to get into your eye. That's exactly what you do with like lists. You say it's the least type containing nil enclosed under cons. In other words, if you give me any type with a pseudo-nil and with a pseudo-cons, if you know what I mean, then I can make a map into it from any list by sending nil to pseudo-nil and cons to pseudo-cons and computing. Okay? So we have that as an inductive type. And then we're going to have a separate thing called path, which internalizes these identifications or paths. And in particular, if I write id A, this is generic in A, and this is not. Path A, actually it will be written slightly differently from that, but I'll suppress for the moment the full notation for that. So we'll have path A, and this is what that type is depends on A. The paths in a type depend on what the type it is, whereas the identifications, which is this given by reflexivity and J looking for reflexivity, they don't care what the type A is, you just look for reflexivity. And then the mess up is you put these two things together. Now, in the math realm, even in the type theory, at the end we will discover that these two types are equivalent in the sense that I was explaining. But equivalence doesn't preserve computation. So what happens is, I can even define something that looks like J on paths, but it won't compute on reflexivity. Because up to equivalence, if I go through the identity, I can get back to a path. But it would have to recognize when a path is what is called degenerate, when it represents reflexivity. You cannot do that. So the computational meaning, if you care about the computation, this separation is inherent. You must make this separation, except in certain limited special cases. So if you're just dealing with function extensionality and OTT, McBride and two other authors, I'm not remembering, showed that you can make these come out to be the same for that limited situation. It does not generalize in the way that I'm going to explain to you. It does not account for univalence. So let me just say briefly, you have to make the distinction. Apart from certain restricted scenarios where you can get away with not doing it. If you care about computation, which being a programming language summer school, presumably you do. Yes?
Didn't you say that they end up being equivalent?
Yeah, they're equivalent in the sense of there being
so
maps back and forth.
So you can bring them back together.
Well, yes, but up to an equivalence. Equivalence is a very, very, very coarse thing. And so it screws the computation. The equivalence alone is not good enough to recover computational meaning. That's what I'm saying. So, okay, I can't say any more, otherwise I'm not able to explain that any further. Let me just state the fact. Okay. All right, so this is what happened. So that's the end of the story. That was that, okay? That's what's wrong with hot. And the other thing that's kind of wrong with hot is you can't explain path in a type generic way. You have to do it by the types. And for that, you need the judgmental apparatus. You have to apply that Martin-Left ninja move of introducing judgments, the idea of judgments as prior to the idea of inhabitants of a type. In a certain sense, setting up a type theory consists entirely of defining the judgments. Then you just pick off the type connectives just to internalize things. If I can have two maps or two terms, one of type A, one of type B, I can pair them up. I mean, the idea is already there that I can have two of them. All right, so I compare them, of course, I internalize it. The idea of entailment is the hypothetical judgment, I internalize it. So all you do is you build a rich enough judgmental apparatus, then all the concepts are there, and then you just internalize them as you see fit. It's beautiful. That's Martin-Left, a great, great, great insight that can only be understood by experience. I believe. I believe from experience. If I just try to talk to my colleagues at CMU who are not like in the area or something, I cannot get them to understand this. Okay, not because of anything wrong with them. It's just they don't have the experience, and it's almost impossible to explain it. Like why it's so important to distinguish entailment from implication. They think I'm like weird logicians who split hairs. Okay, it's not like that. It's a deep and beautiful subject. And anyway, okay, so we're going to apply, so that's my idea. So the idea is that we're going to apply the Martin-Left ninja move, what I want to do. And I've kind of given you the whole story already. Okay, so now let's talk a little bit about paths. And there are going to be two kinds of paths, which are between types and within types. So between and within. And now, because of this principle here, which was analogous to these other principles, in a certain sense, the thing that matters the most, because those are the means by which I can transform a result M from one type to another. So I care about the paths between types the most. And they are induced, so where do they come from? So paths between types. Where do we get paths between types? Well, one is they're induced by paths between elements. I should have said between elements of the index type of a family of index types. So if I have a family, if A is, let's call it I, well, I better not do that, though I gets overworked. I was going to have it be indexed, but anyway, A is an A, and F is a type. Then what's going to happen is, if I have a path within A, will be preserved by F. Okay, that's what's going to happen. So why will that happen? Well, the reason is we set up the meaning of the hypothetical judgment to account for paths as well as, so to say, ordinary elements. This is what is going to happen. So what I'm going to do is develop with you in a, I think, organic way. We start out that all the type theory I've taught you about so far, computational type theory I've taught you about so far, talks only about points. So what I'm going to do is I'm going to generalize to what are called lines or paths, lines between types. And then I will use further argumentation to say we also need lines between lines, which are going to be squares. And we're going to need lines between squares, which are cubes. And we're going to need lines between cubes, which are hypercubes. And then after that, we don't have any words. So we just say n cubes, okay, for any n. Okay, everything, it quickly becomes algebraic. That's why God gave us algebra. Okay, we can picture things in 2, 3 dimensions. If you're really good, Favonia seems to be able to picture things in 4 dimensions. I'm always impressed. Okay, but I don't think anybody can go beyond that. That's completely, Thurston was legendary for his ability to visualize in dimensions maybe up to 4. But anyway, we just use algebra. So the point is it'll be preserved. So that's one way in which you get, so the idea is that somehow, if I write it like this, if I write a path between M and N, I'm going to make this precise momentarily, this will induce a path between F of M, it's a family instantiated, and F of N. And what is the path? It's F of P. Families are kinds of functions that yield types, and they preserve paths. That's all there is to it. It's just like saying they preserve equality, except it's a proof-relevant notion of equality, and everything jacks up because of that. Okay?
I'm sorry, are we between or within right now?
Say again, please.
Are you talking about between types or within types?
This is between, this is within a type, and this is because of that. So this is taking place in A, and this is taking place in what I'll call the multiverse of types. The reason for the word multiverse is, the curious thing about the term universe is that what they exactly are not is universal. It's a crazy thing. It's a collection of types that doesn't contain that very type itself, so it's not universal. And it's designed to be that way, so from a certain angle, it's a weird thing to call it a universe. But then that forces me to have a name for all the types, regardless of whether they are universes or what they are. So I've been calling it a multiverse. If you have a better name, tell me. I don't know. Okay. All right, so
you're saying within is prior to between.
This is the multiverse of all types, which is not itself a type or anything. It's just the multiverse of all types. Just hyphenate that. It's just a reserved word. Okay, multiverse of all types. All right, good. So I'm just giving you a flavor. The other major source of types is is univalence. And the example I'm going to work with is I will look at, all of this can be done in outrageous generality, but I'm hoping that I can pull this off. So let's see what happens. Okay, so I'm going to look at an instance of univalence is the equivalence, given by the equivalence between bool cross nat and nat cross bool. I pick those because it causes certain complications to be trivialized, which helps a lot at the board. Okay? Otherwise, I have to admit to you, it gets technically complicated. And you have to sort of learn to keep your bearings because a lot of stuff is floating around. Okay? But if I trivialize it enough, I can probably do it. And we'll call this line, I'll give it a name, something like swap. Okay? So swap is going to be an identification between two types. And now the leading idea going back, so univalence, which is, what is swap? It's really the univalence axiom applied to the fact that the swap function, which takes m and n and turns them into n and m, is an equivalence. So I'll call that swap equiv. So there's some data which I'm going to suppress the details of, but there's some data. I have to show you that the swap function really is an isomorphism, really, kind of equivalence, okay? That is, if I do it twice, I get the same thing back. Of course, that's pretty clear to you, but there's some stuff involved in actually making that right, okay? So I'm going to suppress it, but I take univalence axiom and I give it the evidence that swap is an equivalence, and then that induces this identification, or this path, which I will call swap. And the idea is that the left endpoint of swap is bool cross nat, and the right endpoint of swap is nat cross bool. Okay, so that's the idea. And then what happens is that, so we package up a bunch of data here, and then the idea is that paths in the multiverse, well, everywhere, but paths in general, but paths in the multiverse in particular, paths induce coercions. Okay, that's the idea. And I'm going to want to be able to do a coercion. I'll call it COE, okay, for coercion. And it's going to be, I can't write down what it actually is right now, but the idea is it's going to roughly take n of swap, and it's going to turn it into a function from bool cross nat. And you think, well, what do you mean turn it into a function? It's sort of already a function, isn't it? Because it's given by this information? Well, yes, but I'll try to give you some flavor. I'm going to give you some indications of why things are not utterly simple-minded. That's the only way I know what to say. If you start with very simple-minded ideas, you quickly are going to run into trouble. So I'm going to give you a little bit of a guide as to how that develops. So let me get to that in a moment. Okay, but roughly, so the idea is that the path swap, which is kind of an abstract notion, induces a coercion by coercion that will map us actually back and forth. This will be an equivalence. Okay, so that's the idea. Okay, so that's how that's going to go. All right, that's what's going to happen. There will be other kinds of identification stuff. So for example, one of the reasons to do this, and that where it becomes a little bit less obvious, and I'll try to bring this out, if I look at the type, the other thing that those paths do is if I look at a type like this, let's say arrow, I don't know, I'm just making up a little example. Here's a type that involves bool cross nat. That will also induce, that will induce nat cross bool, arrow C. And this could reasonably be called, I'll show how it is called that, something that looks like swap arrow C. The reason is that this is the part now I'm going to explain that can be dizzying at first sight. Swap will be a type. Identifications of types will be types. And the elements of those types are going to themselves be identifications within the endpoints. I'll show you in a minute what that means. Okay, so there's a little bit of a dizzying part coming up, okay? I speculate that it will be. If it isn't, good, then good. Okay, so the point is that I can form, just as I can form nat arrow C, I can form swap arrow C. I can form swap arrow swap if I want, because these are types. If swap is a type, of course, I can talk about swap arrow C. And then there will be a question of what is coercion when you want to look at swap arrow C. Well, what does it have to be? It has to be something that when you give it an argument over here, nat cross bool arrow C, You give it a function, and then you want to give it an argument of nat cross bool, and you want to turn that into a C. Well, what do? You swap it, call the function you're given, and that's your answer. So I'll show you how that works. Okay? So that's the plan. Okay, so now I have to explain now, that's like a drawing level, okay, which I think provides a lot of motivation. Let me just check my my work. Okay, good. So now I have to be a little bit more specific about what is a path. Because you see, that diagram when I wrote the diagram bool cross nat, arrow, and then I wrote kind of swap up here because I was hedging exactly on what I'm doing. The nat cross bool expresses kind of two major pieces of information. One is that this is a type, and the other is that, oh, let me drop that. And the other is that, so to say, its left endpoint is bool cross nat, and its right endpoint, oops, that should have said nat cross bool. So how do we do that? So the idea is that paths are traced out by what we'll call dimension variables that inspirationally, analogically, that kind of range over the unit interval, not exactly. This is like an inspiration, okay. The idea is that if I actually had the unit interval as a piece of the real line, then a map from here into some space is, what it's doing is, if I write this picture here, then what it's doing is it's telling us what the zero, where 0 goes, and where 1 goes, and then it's continuous in between. So there's some crazy thing here that's traced out by x. As x varies from 0 to 1, it continuously and uniformly goes from the target of 0 to the target of 1. It draws a line in the space. Okay? When I won't get time to explain it, but when I mentioned loop, we can draw loops in the space by defining suitable types that we map out of. But we'll get to that. I won't get to that. Okay, so the way we do it is, officially what we do is, I can write it like this. Swaps of x is a type parameterized by the dimension variable x. Now you know why all week I was having trouble and I was insisting to myself to write little a for a term variable, because I wanted x to be a coordinate variable when I do dimensions. That's why. Something, you have to have some convention if I screw it up. So that's why I kept, okay, so that's the idea. So swap is a type, and we obtain its endpoints by substitution. So if I take swap sub x, and we use angle bracket substitution, I plug in 0 for x, it ought to be that is, for example, exactly equal to bool cross nat. In other words, here's an x line. It's parameterized by x. I'm tracing out a line of types. The left-hand endpoint of that line is bool cross nat. The right-hand endpoint of that line is nat cross bool. And swap here mediates between them. Now, the way this works, because it's a kind of algebraic or combinatorial thing, you don't know anything about x other than 0 and 1. There's no way to be halfway, okay? Because there isn't any half. There's no distance. There are no angles. So it's a good thing, because you might wonder, what does it mean to be sort of halfway along between bool cross nat and nat cross bool? Well, I don't have to answer that question, okay? That's important, okay? So this just expresses the same as that. It says I have a line, and I'll write it at swaps of x, and then I'm going to arrange it so that swaps of 0 is that, and I arrange it so that swaps of 1 is that. In fact, it computes, this thing computes to that, and this thing computes to that. Okay, so what we're going to have is swap 0 steps to, I'll do it, doing this all very concretely. In the full story about univalence, this is all an instance of it, but it works in great generality. So, but I'm going to be very specific here in the hopes that I can pull off the explanation. Okay, so the first thing is that swap is a type. Okay, that's the first point. And you could say it's a line of types. Or if you want to be more specific, it's an X line of types. In other words, a line of types traced out by X. In a little bit, I won't do it for a few minutes yet, but in a little bit, I'll add X and Y and Z. You can have any number of dimension variables. You have any number of dimensions going on simultaneously. Okay, so that's the idea. Okay, so that's what we're going to want to do. Okay, can I, let me get my bearings here and make sure I know what I'm doing. So I believe I actually said that right, so that's good. So then we have to say, well, if it's a type, what are its elements? What are the elements, in general, of a line of types, but in particular, the line swap? Okay, because you see, it's a type, so it classifies things. So what does it classify? And now I have to remember to get my zeros and ones the right way around. So I'll do, so I'll do this. Okay, well, what they are, in general, are what are called heterogeneous lines. The idea is I'm going to end up saying, I'll give the canonical element, which we'll call swap element, in X of n, which I'm writing here, is going to be in swap X, parameterized by X, if, and then what is the condition? So the condition is going to be that n, let me remind myself here, right, okay, so it's the right hand, okay, n is going to be in A2 cross A1 in X, okay, that's what I'm going to, this is going to be important, and the reasons for that to be important will come out a little bit later, okay, and the critical thing is this. Why do I call it a heterogeneous line? Is my board readable? Let me write over here. So the critical thing is that if I look at swap L0 of n, okay, so here's the thing. There's certain things I have to gloss over. If I take swap L of X of n and I plug in 0 for X, I not only put a 0 here, but I also put a 0 here. Like I substitute this. In other words, if I take swap L sub X of n, it's worth my while to remind you of this, then what that is swap L0 of n with 0 for X. So when I write this operational semantic step, I've already done that. That's how I got here. That's the way I'm supposed to think of it, okay? And the same would be true with 1. This would be a 1. So swap L0 of n goes to apply the swap function to n, which is to be thought of as the left-hand side of this line, the 0 side of that line. So it applies the swap function. And if I look at swap L1 of n, then that is just n. So the idea is that n, the kind of picture that we have for valence is the following thing, okay? The idea is that this will be thought of as a line whose right-hand side is n. If you want, I'll write it n sub 1 to kind of emphasize that I'm supposed to think of this after starting with the swap line parameterized by X and specializing it. So then let's call that n sub 1. And then the idea is here will be n sub 0, but this has to be the application of the swap function to n1. I hope that's right. I think that's right. Okay, so that's the thing that I want to have here. To n0. One of them is n1, and I want to apply it to n0, sorry. Yeah, because the swap function is defined over an n0. If you want to think of the swap type, the way to think about it is, I'm not sure if this is going to help. I will not write this. Okay. Okay, I hope this is good enough because I'm not going to get too specific. So, okay, so that's the kind of thing that inhabits that type. Now, right at this moment, I'm just saying that's the definition. You could very well wonder why that's the definition. I may or may not in this process get to the point where I can show you why it has to be that definition, but believe me, it's forced. Okay, so I will. Okay, so that's an example of a line of types and what it means to have an element of it. And the critical thing is, if I have an element, it means that it's on its zero side, it's in the zero side of the type, and on its one side, if I plug in 1, then it's on the one side of the type. So in this case, the zero side of the type is going to be, A2 cross A1 with 0 for x, and then the one side will be A2 cross A1 with 1 for x. Okay, so that's what I mean by heterogeneous. So let me just double check I've done that right. I hope I've done that right. Okay, and now let me see what's going on here. Okay, so now if we work it out, I'm running short on time, am I not? Oh my God. All right, so let me think about my time. Give me a moment to think about what I want to say. What I want to say next to make sure I say the things I need to have on the table. One moment. Okay. Good. Okay, well, all right. Now let me just mention the following thing. I don't know why I'm having a bit of a hesitation. I think there's something I had wanted to say and didn't say. Okay, but well, we'll figure it out. Okay. So okay, good. So now the thing is that associated with this type line, right? So the idea is lines. Ah, right. Okay, here we go. Right. So now I know what I want to say. Okay, good. So I've given you a flavor about the lines of elements in lines of types. That's supposed to give you a flavor about that. This is the notion of a line of types. Okay, good. So now here's what's going to happen. Okay. So now the general setup is this. Let me just step back from the particular example. The general setup. The general setup is this: is that lines induce coercions. Okay, that's the thing that I alluded to before. So the point type lines induce coercions. Okay, so that's the thing I had before. And in general, we must be able to compose lines. And here's the kind of thing I mean. I'm going to say something. Yeah, let me do it like this. So what do I mean by, let me look at the second. We've mentioned a little bit what coercion must be. So then we want to say something about what does it mean to compose lines. So it must be the case that if I have a line, because there's an orientation, there's an idea of 0 to 1, we can think of it as going this way. It has to be reversible. Okay? So that's part of what we call composition for reasons which I'll allude to and I'll mention in a minute. Okay, so this is still 1, this is 0. If this is a line P, this should be its inverse or reversal, however notation you want to write it, because it witnesses the symmetry of identification. And it must be the case, if I just draw it like this, okay, that I can concatenate lines, so I can take P and Q and R. And now the worry is this. If I concatenate them like this, or I concatenate them like this, and I form either this or this, oops, sorry, or this guy and this guy should be the same. And what does it mean to be the same? It means that there has to be a line between the lines. That it must be possible to sweep this top line down to that bottom line, and vice versa. So that can be expressed in different notational ways. One is to put like a double line here or something. This goes from here. Another is to fill in. And the reason for the filling in, to kind of shade it, is to give you the idea that there's stuff here along which we can deform one line into the other. That's how that's going to work. That gets us to the idea of higher dimensions, because we want to have lines between lines. Okay? That's the critical idea. So in other words, the associativity, okay, that we would need to require, I need to know if you do PQ and then R, or if you do QR and then P in the front, it should be the same. Okay? And the same as that. And there's a very miraculous thing. I still don't really understand this, but there's a very miraculous thing called the Can condition. Okay? Which is, from our point of view, it's a program, okay, for performing compositions that gives us all of this structure, all in one go. And I can show you one piece of it to give you a flavor. What it does is it says, one version of it, this is the most basic thing. Let's introduce two coordinates, y and x. If I have a line between here and here, the Can condition says I should be able to attach other lines at the ends going in the vertical direction, and then I should be able to compose them. So let's call these P, Q, R. And so let me put the arrows in, because it's 0, 1, 0, 1, 0, 1. So they're going like this. So the Can condition, amongst other things, guarantees that that line exists. And in Quark, I can say, what line is this? It's P inverse dot Q dot R. It's the line that goes up here, over here, down here, and that's how it connects them. That's the composition. Which means that it gives you reversal for free, because you can take Q and R to be trivial lines that don't go anywhere, and then you're just reversing. Or you can take this to be a trivial line, and then you're just concatenating, so that comes for free. And then the miraculous thing, it also ensures that we have all of these kind of other lines between lines that we need in order to make the algebraic laws work out as identifications. And then what happens to you is, when we have these double lines like this, then I have an apparatus of lines at dimension 2, and then of course I'm going to have axioms that guarantee, or conditions that guarantee, that the lines between those lines, when concatenated, obey associativity, which is a line between lines between lines. So the line between lines is a square. So the general pattern is the following. So in the Cartesian setup, so in what is called the Cartesian cube setup, we generally have A as a type where actually we do exact equality. Let me suppress that because things are hairy enough as it is. So we have the notion of A as a type in n dimensions, x1 through xn. And we have the notion of an element of A, or really equal elements of A, in n dimensions. Okay, that's the basic setup, where n is bigger or equal to 0. And the critical idea about it is this. As I was mentioning, we start out with points. We then started considering lines. Then we consider two different lines. Now over here, they shared endpoints, but let's just make it explicit. I have another line here. So the idea is that this might be called top and bottom, and this one will be called left and right. And if I have such a square, its boundary are a given, top, bottom, left, and right. And so we can think of this, if we call this guy Q, then the idea is if I plug in 0 for x, assuming my coordinate system goes y and x like that, if I plug in 0 for x, then that ought to be L, because the right side of that square is R. And similarly, the top side of that square, which is 0 for y, is T, let's call it, and 1 for y is b, all right, the top and the bottom. That's the picture that we have. And so in particular, these corners, this corner is going to be simultaneously, well, it's just going to be, let's put a q0 for x, 0 for y. There's an issue to be worried about here. The issue to be worried about, let's just first of all write that down, and then I'll mention an issue to be worried about, which is one of the technical complications of the type theory. But let's write it like this. This is 0 for y and 1 for x. And then this is going to be 1 for y. That's what these vertices are, okay? And 1 for x. And then this is the only thing left. So it's 1 for y, 0 for x maybe. I hope I got that right. 0 for x, yep. Okay. Those are the corners here, and that's there. The one thing you have to worry about, so the worry is this. When I substitute, like 0 for x, it may be that this is a value, but when I perform the substitution, it runs, okay? If I ask for the left endpoint of a line, it's a program, and I say to you, here, plug in 0 for your dimension variable x, compute for me now what the value is there. You have to run it. Okay, so the thing you have to worry about is if I take this guy and compute it, and then compute, let's say, I don't know, 1 for y on here, that has to be the same as if I simultaneously plug in 0 for x and 1 for y and then compute that answer. And that's called coherence. So the idea here is that they're subject to coherence. I can't explain any further in the time I have. So subject to coherence requirements. In other words, the meaning of this is not merely somehow if you plug in 0 or 1, then this is the type. Well, that's true, but it's much more than that. Everything has to fit together in a certain way, and it has to commute with the evaluation. So then there's a whole 5 pages of a paper explaining how that works. So I can't detail it for you. I just want to give you the flavor. Okay, so I wanted to explain about coherence and higher dimensional things. So then we can get squares. So the thing is, I was emphasizing now here with Q, if I start with a square, I can take what are called its faces, the top face, the bottom face, the left and the right. Or I can take the faces of the faces, which are these vertices in the corner. So it has all of that. But another thing I can do with this cube that's very important to understand is 2 other things I can do with the square. One is generally or vacuously extending out of the board to form a 3 cube. Because it doesn't have any z's involved, so I can think of it as having trivial or vacuous extent or empty extent in the z direction. It's like saying when you're drawing category theoretic diagrams, when you do reflexivity. Reflexivity wants to be a map that doesn't go anywhere at all. So what do? You draw it really small, you know. But it's also could be called a degeneracy. The idea is that the point itself is a line, namely reflexivity there. The square itself is a cube. It's reflexivity of the identification of the cube with the square with itself thought of as a cube. Okay, so that's degeneracy. The other is diagonals. I need to be able to plug y and form this line out of that square. Those are the critical, and the diagonal is the critical thing that makes the Cartesian cubes, really. So the big issue is diagonals. And the mathematical part of our contribution is to figure that out. Because it turns out that some of the things I'm describing to you here can be transported into other more mathematical settings of which I'm only dimly acquainted. But the ideas, some of the main ideas we worked out in a computational setting transfer over. So that's kind of good. And the cool thing is the diagonals. Okay, so now back to the chase. So I'm really running low on time. I was supposed to finish probably, certainly by 5, and probably now, really. Okay, so let me figure out what I need to say here. Okay, so the first part of the setup is you have to have this idea of lines and squares and cubes and so on, with this idea that you can take the faces and still get back a valid line or square or cube. Taking faces causes computation to happen. So when you do this, this runs. Okay, so you have to make sure that things are coherent with respect to how they work. And then you get all that apparatus going. Then you have to say, well, so what if I have a line? Well, in order to have one, I have to have the idea that lines induce coercions. Lines between types induce coercions. Lines between elements induce lines between types via families. So I have to explain to you what are those coercions. I can show you briefly, I'll show you one. I'll show you what those coercions are. And you must be able to compose lines. You have to have enough lines. Okay? So this is what you do with a line, and this is, you have to have enough of them. So you can't have a situation where you have an irreversible line or something, or lines that cannot be concatenated. That's impossible. And moreover, that structure has to be well behaved. It has to behave like a groupoid, okay? A groupoid, as I mentioned before, is like a generalized equivalence relation, okay? So I have to say, if I reverse twice, at least up to identification, I have to get the same thing back. So it's just like the group laws. And if I take P inverse and I concatenate it with P, I'd better get a self loop up to further identification. If you do that to all dimensions, it's called an infinity groupoid, a weak infinity groupoid. It's a very fancy sounding thing, okay? But it's just the general theory of coercion. So computer scientists can relate to it in a pretty natural way, I hope, because we want to, it's really just talking about coercion. So I gave you one example with swap. So let me tell you now an example of how we lift that, or how we deal with that. So the general flavor is, and now I will start with talking about coercion from 0 to 1 in a line of types. And I'm going to make that line of types be a function type. So previously, I told you about coercion from 0 to 1 in x.swap of x. And what should that be? That's the actual notation, okay? I have a bound dimension variable, so I'm thinking this is an abstract line. It's not situated concretely in space. It's just a line parameterized by x, which is bound here, so it can alpha vary. It's just a line I can situate in space as I like by plugging in for x. So this should be a map between swap x with 0 for x, which I told you was bool cross nat. And that should be a map from there into swap x with 1 for x, which I told you previously is nat cross bool. So the coercion swaps. Of course, that's why I called it swap. Okay. All right. So the coercion is going to go from bool cross nat to nat cross bool in the evident way. There are lots of evident ways. It all depends on how I define swap equiv. That little package swap equiv, I could come up with some crazy ass things. For example, I could decide just perversely that along the way I also swap true and false. Well, who cares, okay? I will still get an isomorphism, and I can do that if I want, okay? Or I can swap the evens and the odds along the way. Oh, no, sorry, not for nat, but anyway, something like that. Evens and odds, that will work, yeah. Something like that. So the point is that all that information is packaged up in the fact that swap is an equivalence, okay? Then I do that. And then the apparatus operationalizes that, and it does it in this manner. Now let's look what happens at other types, okay? So I can get that example of swap x arrow c. So what happens at other types? So the picture is, these are types that have an x in them, okay? So what should this guy do? Well, let's give it an argument. Okay, where is that argument sitting? It's going to be in the 0 side. This says coerce from left to right, the left endpoint to the right endpoint along here. So what I will do is I will give you an element of 1 with 0 for x. Okay? And what should this guy be? What should it turn into? Well, another way of writing this, actually, I feel like I should do it this other way. Okay, so let me do it like this, because I want to emphasize. Yeah, can you give me one moment? Right, I'm sorry. So this guy, I might have, yeah, I don't know what I just wrote. I might have made a mistake. Okay, so let me write it like this. What this ought to be is A1 with 0 for x, arrow A2 with 0 for x. I'm not positive what I wrote a minute ago. When I was preparing my notes for this lecture, I got confused in this way repeatedly. Okay, so it goes from the left side of this type, which is A1 arrow A2 with 0 plugged in, and it goes to the right side of this type. Okay, so the right side is it's going to take let's call it, I don't know, A1, which will be in A1 with 1 for x. Because, you see, you're given this guy, and what you want to get is something that's in A1, 1 to A2 with 1 for x. right? It goes from the left side of that type to the right side of that type. Okay? So therefore, if I want one of these, I want a lambda, and its type is in here. So what do I do? Well, somehow or other, I want to apply M to A1, approximately. Somehow or other, I want to apply M to something, because I'm coercing M. So what do I want to do? The special case would be my swap X RC. You can work that out. So what do I do? Well, what I do is inductively, I know about coercion for A1 and A2, because just like I built up the semantics of computational type theory when I told you what A1 or A2 means at the level of points, it was in terms of equal things in A1 go to equal things in A2. Now I'm going to say something more. Every type is going to come equipped with coercion and composition operations. It'll be what's called a can type. So I can assume that A1 has coercion and I can assume that A2 have coercion and composition. I'm going to use that in order to define coercion, in this particular case, at the function type. So what I do is I coerce from 1 to 0, that's the important thing, in x dot A1 of A1. Because A1 is in 1 to x, that's the left side here, or the starting point. And if I'm coercing in this line, then I'm going to get something back with A1 with 0 for x, which is the domain of M, so that's good. And it delivers back something which is A2 with 0 for x, which is the codomain of M. And so I have to coerce it back. I have to coerce it from 0 to 1 in x dot A2. And voila, that's how I do it. If you've ever studied subtyping and coercion interpretation, subtyping, this kind of thing will look familiar a little bit. Okay, so modulo some way of thinking about it, but it's basically the same idea. That is our notion of coercion in a function type. Now, unfortunately, I don't have time to do, I set myself up so that I could explain something else, but I won't be able to do it. But notice what I did here. In order to define a coercion from 0 to 1, I also needed coercion from 1 to 0. That's part of the game. So, what coercions do I need? Well, then this becomes the part that I was hoping to explain to you, but I won't have time. We have coercions from 0 to 1. We have coercions from 1 to 0. They have to be reversible. Then comes a weird thing, which is what is called coercion from 0 to x, and also conversion from x to 0. I'll explain what I mean by that in a minute. 1 to x, x to 1, and x to y. I need all of these coercions. This all has to be possible. So let's say roughly what it means. From the left end of a line to the right end of a line, from the right end to the left end, good. From the left end to an x line, okay? So what it means is if I plug in 0, I'm going to get, what's going to happen is we're going to have the following thing. In fact, it's the reason why the elements of the swap type were defined the way they are. And I'll just draw the picture like this. If I look at COE, let's say 0 to x, in some type, okay, y dot b here, okay, this is what I want, I think. Let me think about that. I want its left endpoint. This is, the important thing is it's a line in x. So I want its left endpoint to be the coercion from 0 to 0 in y dot b of m, which we are going to guarantee is m. If you try to coerce from where you are, and where you're going is exactly where you are, you return the thing you have. That should at least stand to reason. It's actually pretty much forced, but it should stand to reason. Okay, so if you're coercing, so the left endpoint of this line is m, and the right endpoint is a coercion from and y dot b of m. So think of b as swap x. So let's say that that's swap x. And remember what this means, it swaps the components of m. So I need a line whose left endpoint is one pair and the right endpoint is the swapping in the other direction. And where am I going to get that? I'm going to get that out of m because the elements of m in the swap type are such lines that have swapped endpoints. This may be too tricky to catch that on the fly, but there's a very important point here is in order to compute the COE from 0 to x, that computes to something. Evals to something, all right, something, which is derived from m itself. And That's why, this is the secret to why swap L is defined as it is. And that I'll say no more, okay. I had hoped to amplify this point because it's kind of cool to see how this stuff works, okay. But in the end, I need all of these coercions. I was not able to explain them because I've now run out of time. But if you want to puzzle for yourself, without other knowledge, you won't be able to solve it probably. But puzzle for yourself what happens if this is a dependent type. If this is A colon A1 arrow A2, where the A can occur in A2, something is going to go wrong because the type of this guy will have that in it. And now you have to figure out how to recover for that. And the trick is, for dependency, you need this idea of CoE1 to, it happens to be CoE1 to X. If we're doing, you need the, which is in A1 of something. Maybe with that hint and a picture of what such a CoE looks like, you might be able to at least formally guess what this is, but you can look it up in the paper. So I don't want to overtax your patience here. So can I figure out? Okay, I want to figure out how to stop. Okay, so that's how to extend the dependency. I spent hours and hours and hours just writing out all the cool things I wanted to tell you about, but I don't have the time to do it. So you can see what I'm paging through here. Okay. All right. Okay. So let me just wrap up. So I hope that gives you a flavor. You start out with something naive like you want to take this identity type which has this J operation and you kind of want to throw in identifications such as univalence or function extensionality, and you don't know what to do with that operationally. So the ninja move is to make the judgmental structure explicit, and then we'll internalize that judgmental structure into the types, and the chips will fall where they may. The way we do that is we introduce the idea, first of all, of a line. So we can have a line connecting a line of types. That was univalence as an example of a line of types. I gave you swap as an example of that. And then you say, well, but what's the point of having such a line? Is to be able to coerce. That's what the J applied to UA wants to be a coercion, but it can't be because poor J is independent of the type A, but the idea of an identification depends on what type you're in, and you have this conflict. So coercion is the way to resolve this, okay? So coercion works with paths. The J works with this other type id, and they just don't go together, okay? That's in the general case, they don't go together when you have univalence. So what you do is you develop this idea of lines, and as soon as you develop the idea of lines, you start worrying about having lines between lines, and it can come up in various ways, and I used one motivation for it here. So you're immediately into squares, and as soon as you're into squares, in for a nickel, in for a dollar, so now it's squares and cubes and hypercubes, and there's no stopping point, it goes forever. And so now types have an infinite dimensional structure. Okay, they have in principle cells at every dimension. Certain types can be characterized by their higher dimensional cell structure, and you can say that, oh, they're degenerate all the way from dimension 1 up or something. You know, things happen, and we can characterize n types as one for which after n dimensions they become trivial. That's one like enterprise that people are engaged in to figure for various reasons that I can't explain right now. So that's the shape of it. And then you have to ensure, once you know about coercion, you have to define what coercion is. You have to define quite a hell of a lot of notions of coercion in such a way that it's all coherent. So the other thing is that these guys all have to fit together, because if I take a 0 to x guy and plug in 0, it had better do the same thing that 0 to 0 does. And if I take the x to 0 guy and plug in, 0 or 1 here, it had better do the same thing that the 1 to 0 coercion does if you defined it separately. So then it gets to be quite the hell of a mess, okay? But we've worked it out. I mean, it keeps getting simpler every few weeks. We get it simplified. We've greatly simplified the treatment of univalence just in the last month or so by suggestions of Anders Morpert. So it's a very, but I just want to tell you, this is the kind of thing you have to do. Then you have to do compositions, and you have to have these kind of U diagrams in some generality, and I wasn't able to give you time. But the way you do this is, is by constraints. You basically say, I start with a cube, in this case a line, and I attach other cubes along it in such a way that they all fit together. Like this corner is the upper edge of that guy and the left edge of that guy. This corner is the upper face of this guy and the right face of that guy. You have to have adjacency requirement. If you're a multiple dimension, then they have to fit together. Imagine you take a square and you attach a left and right side and a front and back side. The bottom is empty, and the can composition will give you the bottom face of a cube that also has to be there. Okay, so it's a requirement that you have enough cubes. So you have to have enough cubes. Now it becomes the mind-bendingly difficult thing. Oh, but the multiverse has to have these compositions, which means that the compositions of lines or cubes of types have to again be cubes of types, and they have to have elements with coercion and composition. And that's the point where it becomes insane, I have to tell you. Okay, it becomes very complicated to work it out. It's all done now, and Kokon and his group has done it with a different notion of cube, but very inventive ideas to make that work out more easily than you might think. And we have done it in the case of Cartesian cubes. So I'll just sort of just make that statement. So that's what happens with coercions and composition. And then you have a full higher dimensional type structure that gives computational meaning to hot by distinguishing paths from identities and getting that all sorted out. So that J works the way it works, but it got nothing to do with J view. Don't worry about that. We instead have path structure. And in fact, what happens is the hot formalism becomes an uncomfortable peephole that only lets you look at points. You can never, ever look at lines directly. You can only look at them once they've been quoted into a path type. And that's clumsy as hell. You don't want to work like that. So the current thinking is, what you want to do is work in the cubical type theory. Okay? And you work with the cubes directly. Forget the old formalisms. Those are done. Okay? That's our current operating assumption. We are working in implementations of, if you look at redpearl.org, redprl.org, that's our first cut in implementation of the higher dimensional computational type theory. There's another one called redTT under development, which I don't think pretty sure is not available publicly yet. And we've been working closely, so let me give credit. My students, Carlo and Julie, Favonia Kunbang-Hu, Favonia, better known as Favonia, he's one and only Favonia, and Evan Cavallo, John Sterling in particular in implementation, Anders Morperg visiting us as a postdoc from Kokon's group. In Kokon's group I mentioned yesterday, or day before, Terry Kokon, yes, there's Simon Huber and Anders Morperg, who's now our postdoc, and also Cyril Cohen, who personally I've never met, but there's another fellow there. One day I'll meet him. And those people have been extremely, those are the central players, I think. I hope I'm not being unfair, I don't mean to be, on developing cubical type theory. And so like you should know that. So I'll mention that. So okay, so that's the state of play, and like very absurdly advanced type theory in some respects. If you ask me what is it all good for, well, I don't have a good answer for you. Someone was asking me this, and the only thing I can use a cheap trick, which was, well, you know, in 1980 when I first heard about type theory, and heard about the idea that proof should be programs, goddammit, and the law of excluded middle is not valid, I was delighted, because that's what I thought. I just didn't know why. I hated proofs by contradiction. I thought they were the biggest cheat in the world, and I just felt like it shouldn't be allowed. It's just not fair. And then Constable told me, you're right. And so I was like, this is the best thing I've ever heard of. So in the beginning, when developing type theory, we didn't know what it was good for, to be honest. You know, there was some idea it must have something to do with programming. Now, like, you can't even imagine a programming language without types. Oh, well, you can, actually. But, you know, that's the way the world evolves. So, okay, so anyone with an education like they get at OPLSS knows perfectly well the importance of types. So I can make a cheap argument, which is that, well, maybe this higher dimensional structure will, in ways that we cannot envision, work out in 30 years' time, or 40 years' time, or 50 years' time, or if I'm not lucky, never. But work out and we'll figure out what it's all for. But it's not really driven by that. It's driven by, like, considerations of a very general sort, that structure that is there, and trying to understand it from a computational point of view. So that's the thing. So for me, that I think is cool, a nice way to close up summer school on programming languages. this is kind of advanced programming language research. So this is, in my mind, as terms of my own interest, this is what it should be. Like, this is what we're doing. PLs is not about some popularity contest and people with great charisma convincing everyone to say things that are even wrong about how cool such and such a language is. It's like, you know, there's some actual facts to be figured out, and we're trying to figure some of those out. So that gives, is just one direction that some small number of us have been pursuing, so that's that. Okay, good. So that brings us to the end of the summer school. Maybe we'll just finish this and I have some more to say. Sorry. So I'm done. Yep.